So actually I already showed you a recurrence network. So recurrence network is the idea that you can turn a time series into a network. So there are other ways to deal with time in networks. So like the Game of Thrones I showed you, you can just for each time point perhaps create something and make an animation or something like that. But that's not what recurrence networks do. They will take each data point as a node, and whether you draw an edge between nodes is decided by whether the value you observed at this node is actually recurring. Right? So this is actually a recurrence network. And this was the story that we looked at when we were talking about the recurrence analysis, and the second story had many, many more connections. So what can we do, what can we calculate if we are considering these networks? Well, we can calculate the degree, right? So the total degree is just counting how many connections do all the nodes have in this network. And then, of course, here the degree should be higher in this one, right? So you can also, from the network perspective, you can distinguish between these two time series in terms of degree. Actually, if you would divide this over the amount of time points, you would probably get the recurrence rate. So this is a data set collected by the J. Delinière from France. And what you see here are 4 participants, and they were asked over a period of 512 days. Say it correctly?
It was twice a day.
Right? So it's not 512, but half, 256.
No, it was twice a day for 512 days, I think.
It was 512 days. Oh,
yeah. So 1024.
Yeah, that's correct. The total number of data points is 1024. And there are 6 variables here. So perceived, it's about perceived strength, attractiveness of the body, perceived fitness, sport competence, physical self-worth, global self-esteem for participants. And in the original article, the goal was to do these scaling analyses and show that the sequences here are not, you cannot think about them as like random stuff, but you really need to consider this to be a complex signal. So they have. So these are sort of the conclusions, right? So individual behaviors share common dynamics despite superficial differences. From this perspective, the richness of the individual data sets can reveal dynamics and is more crucial than the number of participants involved in the experiment. So that's kind of the point they're making here. You know, if you measure long enough, then you can get some interesting results. So one of the things I did, so I analyzed this data set, and it's in a paper that's coming out very soon. And one of the things I tried to do here is, I tried to do a number of things, but one of them was take into account this phenomenon that basically what you're doing when you're asking about these ratings is that you're probably, what people are doing is they are evaluating what they are doing relative to a shifting mean level, right? Stuff can happen. All of a sudden you can get food poisoning, and then the range of the scale will change. So what I came up with is something called a change profile. Basically what you do is you take just the mean of a period of time, could be a week, could be longer, and then calculate the moving average, right? And then subtract the ratings that people give from this mean. So this means as if to sort of compensate for the fact that they might be evaluating how do I feel today with how did I feel last week, right? So that's sort of the idea here. So you just subtract this from this moving average, and then you take the cumulative sum. So here you see for this first participant, I don't know exactly which variable this was, but so this would be the original range, right, from 0 to 10. This was a visual analog scale. In gray you see the original time series, and then in red is the moving average. And then the blue thing is the change profile. So for this first participant, it doesn't actually show a lot of large shifts in the rating behavior. So the score, the value really stays within this 0 to 10 range of the original scale. But here you can see, and this is not at all, at least not to me, quite obvious from this original series. So I think this represents the fact that this person really went to a completely different dynamical regime in answering the question. So and this is reflected in this change profile by this level drop here, right? And here there's also a level drop, but it's not as extreme. And here the jumps. So basically, what this transformation does, it does if there are changes in response patterns with respect to the mean level, it sort of exaggerates them and puts them on a different level here. And the reason why I want to do this is because I'm going to do recurrence analysis. And so I'm not interested in, so here we have, for instance, maybe the value like 2 or something like that. That is repeated here. But I think that this 2 is very different from this 2. Because this was like a sort of accidental thing. Maybe it's maybe one observation, but this is a completely different dynamical regime. So what this transformation does, it just puts this on a different level. And this will now be a recurrent thing if you do recurrence analysis. And this one will pop up also, but you will not have like you don't have to be concerned that the radius here will give you recurrences with this that you might not be interested in. But here it might not be so bad because I think this might actually be just one dynamical regime that this person is displaying. So it doesn't solve everything. It might not even be the best way to do this. Yeah, you can think of other types of ways. I'm just using a fixed window, sliding it. But you can have varying windows. You can look at autocorrelations maybe to decide how long it should be, all those kinds of things. Okay, so we have those data. What I'm going to do now is I want to create a network out of this. I don't want to do recurrence analysis, I want to look at the networks. But the first steps then are actually very much the same that you would do with the, if you want to do RQA. Yeah, this is just listing again why you would want to do this maybe. But the interesting thing here is, which is a little bit different from RQA, is you can do, you can analyze what's going on in multivariate time series. Of course, RQA on the multidimensional, that's also, multidimensional RQA is also doing, dealing with multivariate time series. But if you create a network for each of these variables, you can then add them together in like a multi-layered network, and that's the thing that I would like to demonstrate here. So again, we calculate this distance matrix based on parameters, false nearest neighbor analysis, delay, and then pick a threshold in order to create a matrix. Or at least this is what you would do for the recurrence analysis, right? We have zeros and ones, and then, yeah, you could already create a network out of this. This is just, like I showed you in the very beginning, you can interpret this as an adjacency matrix, and then represent this as a network by saying that every node is just a data point, and whether there's a connection or not is decided by the fact whether there's a 1 there, whether there's a recurrent point. So here I chose a recurrence rate of 5% again. This means that the degree that I will find should also reflect this 5%, because I'm only allowing a certain number of edges. So the total degree of the network will have to be related to this number. Now if you want to know everything about recurrence networks. Again, these people from the Potsdam Institute created a Bible reference work in physics reports, just like they did for the recurrence analysis. They now have done it for the complex network approach for the recurrence networks, and it's also like 100 pages. So, yeah, but they are very thorough and they cover lots of things. So they explain how this would work for their field also. Observe data, reconstruct state space, make a recurrence plot, make a recurrence network, get measures, think about what's going on with the Earth, and then do other research. That's basically what they are doing. Well, but the idea is, of course, you can see, turn the recurrence plot into a network. And then there's lots of stuff coming out on how to extract measures, what might be the best procedures. And what my problem was with these representations, so this is, for instance, a network representation of the Lorentz attractor. It looks beautiful. This one as well. But we are interested in figuring out when certain things in time are happening, right? And if in these network representations, they sort of destroy the temporal information that is in the data. So I wanted to think about a different way to represent these networks that keeps the time also into account, right? So now comes the part where you can just look at pictures. So here we have, for participant 1, we have recurrence networks of all these different variables of self-esteem that they made. And this is not exactly, no, I didn't put it up there, but this network is weighted, but it's not represented here in this graph, so it's not that important. But so here the time series begins, and then these are all the time points, and so in this spiral we get to the end of the time series. So it's not 1024 because this represents the reconstructed attractor. Then if and these distinction in these epochs is just automatically, so it's just done to get a nice distinction in different time periods. So now, interestingly, all these time series, also from the different participants, they turned out to have like this 1/f noise structure in them, right? So the fractal dimension is all like 1.2, sometimes a little bit less, but based on the fractal analysis, you really cannot learn something about different periods where different things might be happening. But you can already see that for this variable at least, you know, here there are hardly any connections in these two regions. So when you see a color here, it means that the edges are connecting to the same spirals, to the same epoch, which means they're pretty close short-range correlations. But you can see that there are for different variables, you have different dynamics going on, some with extremely long-range correlations. So this is just one participant. Here's another one, and you can see, even though the correlational structure, the fractal dimension might be 1.2, you know, there's different things going on here with respect to the other participant. And here it's even more extreme, which here it appears to be the case that most of the dynamics are actually going on in the first half of the year. And so on. This is again different participant, participant 4, wildly different dynamics, I would say. So here you can see this. So this is for one variable, for the perceived strength. And here are the fractal dimensions, 1.2. So they're all, if you round them, they're all 1.2 basically. But that doesn't mean that the dynamics, if you look at when is stuff happening, are the same here. So they're very different. And just using fractal dimension doesn't give you this information. So, of course, there are different types of spirals. This is just an example. Again, the same participant, one variable, global self-esteem. Here I reversed. So now one starts here and you go inside. And you can use these different types of layout make accents on different periods. So here you would have the last period is more present, right? And here the first period, and that's very beautiful. Anyway, if you calculate now these network measures instead of recurrence measures, you can see that at least some of them can distinguish pretty well between the participants. So the SWI is the small world index, which is an indication of how scale-free these networks are. So if they are above 4, they're scale-free. But as you can see, they are very much small world type networks. And they can be used to distinguish these things much better than you would be able to do based on just looking at the fractal image. So some more pictures. I've shown you this data set, which is this experiment where the depression medication was reduced. So we can also make graphs of this, but now you can sort of indicate the phase of the experiment, right, in the spiral. So here we have the start, the baseline, and then the start of the double-blind period. Then the reduction starts, and then and so on. And you can do this for different types of variables. I feel down, feel relaxed, and you can see lots of different things going on depending.
And now sleep.
Looking forward to this day. I slept well. You can do something like this. And then, if you use Matti's data, you can do something like this. This is just to show you. I'm creating a weighted network here, which means normally in the recurrence plot these would be black, but now we don't have ones here, but we have actually recurrence times, which means how long does it take for this value to recur, which means so you have an edge, you have a node here and it connects to somewhere here, and then the weight of this edge will be how many time steps does it take before you get to that node. And this actually tells you something also if you then make these power law relations that I showed you that are so characteristic for the scale-free networks. You can actually get an idea about the fractal dimension also based on these network properties. If you look at the slides, I will put them up later on. You can see that I did some simulations with that, and it actually pans out pretty neatly. So let me go to the last, really last part of this workshop. Oh. Because I told you what you can do is, so you have now for each participant these different networks, these different recurrence networks. You can add them into a multi-layered network. And usually what is done is, what people will do is they will then analyze whether there's a structural similarity between those different networks. One way to do this is to look at the interlayer mutual information, which is basically looking at the degree distributions of all these nodes and then figuring out, is this sort of the same or not, basically. And these multiplex networks look something like this. So for each participant, you have here each variable, and then the connections between those networks. They can represent different things. Here they represent average mutual information, and you can see that. So this is for the entire time series, but you can see that there's some different dynamics going on. So here there seems to be. This was like global self-esteem, physical self-worth. I don't remember what this was. Well, something.
Perceived fitness?
Perceived fitness, yeah. So apparently this person is the global self-worth is at least associated with how they perceive themselves as being in sports. I think, yeah, this was sports. Well, something like that. But you can see different types of structures in there. And some of them are very connected. But what you can also do is do a windowed analysis and sort of figure out how these things change over time in this multiplex network. Oh, I could have increased the frame rate a bit. But anyway, you can do all these kinds of dynamical analysis then on the way that these mutual information is changing.
So in that animation you had, did you have a sign on the mutual information?
No.
What's the blue and red?
Well, it's just the value of the mutual information. So high would be blue.
Ah, okay, right.
So, but here you see, like, so these are these are just the values of the different variables, and this is then the mutual information of the interlayer network. So the averaged mutual information time course, and of course, well, this is not a clinical study, so we don't expect any phase shifts. But you can imagine that this might also be an early warning signal detector. You could say that there's kind of a different level going on here, but I don't know enough about these subjects to be able to say. There's another measure which is called the edge overlap, which is looking at, of these different layers, how many of the edges are actually the same in these networks. And that's a different measure you can calculate. But as this is kind of new, you can imagine that we can now have a whole new zoo of complexity measures based on multiplex recurrence networks. So the take-home message, maybe for the entire course even, is actually the first one should be look at time series, collect time series, and then if you have lots of data, don't go aggregate them. Right? Because we have all kinds of nice techniques that you can use to first analyze and then maybe later aggregate what is going on. And if you have multivariate time series, we use multiplex recurrence networks and not these statistical network models that actually require you to average out all the dynamics that you have observed. So, thank you. If there are any questions, I'll be happy to answer them. And otherwise, we're done. Yes.
Yeah. Mine is a pretty general question. I have two. The other one is, has someone modeled real-time macro social psychological operational logics or schematic dynamics in a very ambitious way, like trying to build some kind of a general basic framework?
Can you give me an example of what that might be? I don't know.
Interactions in some very well documented and known social actions that you could use as a base for uniting a multivariate or multi-level model.
Yeah, but what would make them social psychological? I mean, because we do client-therapist interactions.
Sorry?
We do client-therapist interaction.
Well, yeah.
Or parent-child, or right. So the measures that we use to figure out whether who would benefit from the intervention, that was parent-child interaction, and of course part of the questionnaire here, but that's not really looking at the interaction, but we also do like video analysis of interactions. Have people stand on Wii balance boards and do something together, and then look at how they synchronize, those kinds of things. Yeah. I don't know if that's what you mean.
No, maybe I'm looking for more like something like these nodes would be updated in real time, and their relations would be described somehow based on social psychological theory.
Anything that you can think, so if you, anything you can think of as nodes, so if that would be people, and if the relation between nodes, what you put in there is you're free to choose, right? So you can choose something that matters for your field of interest. Yeah, that's possible.
There are these guys who are trying to build this peace machine, which is kind of AI based. system that would allow people to enjoy better communications and so forth. So that's why I'm asking if there is some social
Well,
psychological base.
There are lots of
knowledge.
people applying these things. Twitter conversations are analyzed using networks, lots of stuff. But I don't know if what you're looking for specifically is there. But I'm pretty sure you could do something like that.
Yeah, in theory.
Yeah.
And then the second question is about the best practices of conducting complexity science projects. Is there a handbook of some kind, or because there are so many variables, it would make sense to
There are a
not do
number
all
of-
the mistakes yourself, but rather follow some path. Somebody who has some experience.
Yeah, I promised to put up some links to things on the website. So one thing I will put up there is a link to this webbook by the NSF, free webbook about a number of these techniques and what you might do. So that can be helpful. And then there are some tutorials for RQA I could put up. Another one is we had a research topic in Frontiers Journal about the scaling analysis, which is also a best practices type of setup. So yeah.
Super cool. Okay.
Yeah, I'll put that
you.
up on the website.
It's been an amazing 3 days. There's so much stuff that no way I can take it all in.
No.
It gives a general picture.
That's normal. That's normal.
Yeah.
but yeah, one of the points is of course to show you that there is really a lot out there, and sometimes people pretend that that's not the case. But there's a lots of stuff you can do, and because other scientific disciplines also deal with complexity, right? Just like we do. And I think it's better to face it head on than to pretend it's not there.
Yeah.
Several technical questions. So if I have time series, can I, using CastNet, diagnose the presence of 1/f noise somehow?
Yep. You can. You want me to show you?
You would?
Yeah. Maybe do go back to the mirroring, right?
And
No, so
also-
there are a number of category of. Wait a minute, maybe I can do this even better. I do have to take the mirroring off. Mirroring on. Yeah. So CastNet. Here we go. So here you see a list of all the functions that are in CastNet, and then there's a particular group of functions which start with FD. Yeah. So for instance, suppose I would like to do calculate the fractal dimension based on there we go. Based on spectral analysis. You can use FD underscore PSD. So I'll show you how this works. Let me have a new script here. So suppose I have again a random series. Oh, that's a lot. Sorry. Wait a minute. This. I could just type FD underscore PSD y. And then it will tell me that the slope in the power spectral density is almost 0, which we would expect for white noise, and the associated fractal dimension is 1.5, which is the fractal dimension for white noise. You can also get a plot. So here you see, this is a spectral analysis, so here you have the frequencies, here you have the power, and you can see there's no relationship between frequency and power, so there's no power law here. But let's see what happens if we do the commutative sum, where we have Brownian motion. Whoa. So now there is a relationship between the frequencies in the signal and the power, which just means this is a very slow wave, right? So there's a low frequency which has a great influence on what on the shape of this waveform, yeah, it's a fractal dimension of 1.1, which means it's almost like a line. So let's see if that's true. Yeah, so it's very line-like compared to the white noise, of course. Which is more plain filling. So yeah, and then there are a number of different techniques there. The trended fluctuation analysis, standardized dispersion analysis.
Oh, thank you.
And the data preparation for those analyses, do you have a source for those? Because we didn't go through.
Yeah, I'm making a vignette about that, which will be on there very soon. Yeah, yeah. Some of these they require different types of data preparation. The trended fluctuation analysis doesn't require any. More? Well then, I think thank you very much for your attention and enthusiasm and openness, right? Because that requires some openness to be receptive for this type of information. And yeah, you know where to find Matti. If Matti doesn't know, he'll send you to me. No, you can of course always contact me if you want to apply this or have questions. And I hope you will use it in your work.
Thank you.